All right, well, we are at time, so we will get started. I'm sure people will, sorry, I just moved a step past. I'm sure people will join us as we get going, but I don't want to keep us past time. So thank you, everybody. If you want to turn off your mics and cameras, or I can do that for everybody, but thanks for joining us today.
All right. Thank you, Gabby. So good afternoon, good morning, everyone. I am Andy McMahon from Central Carolina Community College. I'm one of the co-PIs on the Create Energy Center. Today, it's my pleasure to introduce our speaker, Jason Oliver, who will speak about architectural design in the age of building and energy modeling. But before we do that, I would like to take just a moment to make sure everyone is aware of some of the resources and opportunities that are available through the Create Center. All of these things that I speak of in the next moment or two will be are able to be found on the Create Energy website, which is createenergy.org. Specifically, we have a few upcoming events I'd like to make everyone aware of. On the 17th, Monday, the 17th of November, we will have a coffee hour hosted by Jennifer Clemens on how people are using AI in their courses and in their jobs. It's an evolving topic. I think all of us have probably had some experience with. All of us can probably share some lessons learned and learn from others. So a really great topic, I think, for an informal conversation amongst faculty of how we're using it. We also have a webinar coming up November 3rd. This is in partnership with our friends at the Earth Center. There was a collaboration between Create and the Earth Center to take an existing curriculum that was built a few years ago by Scott Liddicoat, and we have worked to update that with a few more interactive, online interactive components to make it a little bit more up to speed and a little bit more engaging for students. And so we're going to preview that during the webinar. If you'd like to also join us for another webinar in November, not quite sure of the date at this point, but the Create Center's PI, Ken Walls, and one of our other co-PIs, Dr. Kevin Cooper, will present on the considerations for installing electric charging stations at your college. In addition to that, we have a number of in-person opportunities coming up, mostly in the summer of 2026. You can see the menu of offerings there at the bottom. We have them essentially throughout the country. These are largely in person, minus the first one that is clearly identified as virtual. Those are not able to be signed up for quite yet, but come back or check back in about January, and we will have methods for getting signed up for those events. So with that said, I do want to introduce our speaker for today, Jason Oliver. Jason is the chair of Architecture and Interior Design program at the College of the Canyons in California, as well as a licensed architect in California for over 25 years, and a lead accredited professional in building design and construction. His experience as a practicing architect includes being on design teams for numerous projects in both the United States and Japan, ranging from small residential additions up to international airports and major hospitals. Jason began his professional education studying architectural drafting at Los Angeles Pierce College in the early 90s before he transferred to earn a bachelor's degree in environmental design and a master's degree in architecture from the University of Colorado. He is an active participant in a variety of nonprofit educational outreach organizations, including the Santa Clarita Environmental Education Consortium, the Southern California chapter of the National Organization of Minority Architects, and the California chapter of the U.S. Green Building Council. Recent international collaborations include student-focused educational projects with colleges and universities in Central America, South America, and Europe. As an educator, Jason focuses on the synergy between sustainable building design and every phase of a student's learning process. Jason, thank you for being with us today, and we look forward to learning from you. With that, I will pass this off to you.
Great. Thank you, Andy, for the introduction. Good morning, everybody. Hope you're doing well. So I wanted to talk about a lot of the kind of transformation that's happening in the architectural industry, specifically being driven by the technology in building energy modeling, or sometimes what we'll refer to as performance simulation. So most people, if you ask the average person, what does an architect do? And I think the perception is that architects create forms, we create spaces that are used to serve a client's need in whatever form or shape that might be. So in the case of a house, obviously, to provide a habitat for people to live in, an office building or a school, of course, has uses and functions that are supported by those forms. So in general, architects provide functionality and safety and comfort for the occupants of a building. But the role of the architect has changed quite a bit in the 21st century because building projects are getting much more complex. Architect's role is I think, more accurately now described as being a service professional, um, and more tied to client outcomes, measurable client outcomes, and that we're a partner with them to achieve whatever their goals are, if it's a business or, again, in the case of a house, and so we're not necessarily just providing drawings or a design, but we're actually um, providing outcomes that are a product of the design process, the sort of problem seeking and problem solving process. And so we're going to look at how performance simulation has enhanced the value of the design process for a project, and how architects now are able to more accurately predict and provide confidence on a project for the outcomes that may be necessary. So we're teaching students at College of the Canyons and at many universities throughout the United States. They're starting to use building energy modeling um, in a way to create high performance buildings. We're using an iterative, data-driven process now that didn't exist, up until maybe 10, 15 years ago, and that's because of the computing technology that's available. So that's evolving our methodologies and the sort of digital performance simulation that we can do. Um, so architects are expected now to bring sort of an insight and an expertise to a project to allow, through these tools, a way to visualize new opportunities and possibilities, as the project navigates the sort of complexities of the design process. So obviously architects, like all building professionals, have to do their work in compliance with various regulatory codes, various industry standards. Here in California, we have the suite of Title 24 codes, the building code, energy code, the plumbing code, mechanical code, so on and so forth. And we also have industry standards. ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Professionals, has a whole bunch of standards that are in many ways tied to the codes, and they inform us about different performance for systems in a building. So it might be the ventilation for a building, it might be the thermal conditions in a building. Um, and so traditionally, architects have kind of kept an arm's distance from actively involving themselves in these more technical aspects, the sort of architectural science or building science, leaving that to consultants, mechanical engineers, electrical engineers, various experts, that's kind of their silo of expertise, and that the architect consults with them when they're designing the envelope of the building or laying out the building. But it's been not so much an intimate collaboration, which is what's necessary now because of the ever stringent environmental and regulatory standards that a building project needs to meet. And so there's so much science that goes into designing a building that now needs to be considered early on. That a lot of this these considerations simply can't wait till the 11th hour of a project, after it's basically designed and all the leverage points are already exhausted, to make meaningful change, to make a building more energy efficient, more comfortable for the occupants, more cost effective. And so in the exhibit on the left, where we can see some, various climate variables that affect comfort, temperature and humidity and solar radiation, for people, we vary our clothing based on, what are the conditions of the weather that day. We put on a jacket or take off a sweater, or, dress accordingly. And even our activity levels, we will, moderate based on those conditions. Well, what about a building, which has basically the same climate variables in play? What are the regulating factors for a building that we often think is, very static? And so not only are buildings needing to be more responsive to the environment in order to meet, the various code requirements, but we're finding that through simulation, we can predictively anticipate more accurately what, how a building can actually respond to the climate in a meaningful way. So this is a diagram that I show students that, kind of illustrates the various environmental factors, the external ones that affect the building as far as heat transfer, and different environmental conditions that a building can respond to, the envelope of the building, or the way the building's configured or constructed, the various assemblies and systems that go into a building. And so we've moved into a point now where, with the simulation technology, just taking a couple of those factors, which would be solar radiation, that as the architect is designing the model, and more often than not now, in close collaboration with mechanical engineers and electrical engineers early in the process, we can start to simulate and quantify a lot of the impacts of these environmental issues. So, like for instance, solar gain, the solar radiation that's emanating from the sun, either directly or indirectly, because maybe it's being scattered by cloud cover or reflected off of, surfaces nearby. We can simulate that solar gain, heat gain for a building, and sometimes we need solar gain to heat a building up in the wintertime in cold climates. But where I'm at in Southern California, we're often trying to combat solar heat gain, excessive solar heat gain, so shield against it. And so we can, in the case of the level of a room or individual surfaces, we can start to use this data to inform the geometry of a building, that sort of exterior envelope, and to inform us of the need for shading, or to inform our decision making about the percentage of fenestration or windows. What we look at is, for instance, the window to wall ratio. How many windows do we want to have on a particular exposure? And part of that decision-making process involves, how much solar heat gain do we want to admit into the building? Because windows are obviously a place for heat gain to come in more so than an opaque wall or a solid wall. We're making those decisions as architects in conjunction with a lot of other factors. The client has, different ways they're going to use a building. Maybe they need natural daylighting. Maybe there's views that they need to take into account. So this data is not necessarily driving the design, but it is another component of intelligence, that comes into this design process, this decision-making process. So here's a project that was done in the kind of early 2000s, designed around 2008, 2009, that started to, this was in Southern California, and it took into account the climate, but it did so in a much more analog way, that it wasn't using performance simulation. And so it wasn't very, it had to sort of overcompensate for the fact that, in order to shade the windows, in order to provide protection from the sun, the geometry got a little extreme. It was used aesthetically. It became a part of the character of the project, but in a certain way, it wasn't, doing what we might do here in 2025, with a much more informed process using digital simulation. So, obviously, solar radiation is one of the critical environmental components that architects need to use, and throughout the globe, particularly in the tropics, or the sort of middle band, north and south of the equator, solar radiation is a big part of what we need to be aware of. And so the computing power allows us to do that. We're able to very accurately simulate the solar angles throughout the year, throughout the day, and see how they're going to impact a space as far as heating and cooling load. So for this retail project, at that time, we were doing very simple sectional diagrams, like you can see on the left here, where we might plot the summer sun, which is going to be higher in elevation at noon, the winter sun, which is going to be lower down. We might actually want to admit some of that winter sun, but there wasn't much beyond these diagrams to inform the solar radiation impact on the design of the project. But it was kind of neat to see it, built and kind of get a sense of the natural daylighting that came from the space. But that wasn't something that was predicted at the time. The computing, potential wasn't quite there. Fast forward 15, 16 years now, in the architectural industry, we're starting to use a lot of tools that do simulate environmental performance. So here's some of the commonly used platforms at College of the Canyons. We teach two of them predominantly. We use Autodesk Revit, which has a environmental simulation tool called Insight. And then we also have been using a new software for us, which is IES Virtual Environment, to do a lot of the calculations and performance simulation. Some of these are publicly available, developed by the Department of Energy in the U.S. Some of these are private, industry software platforms, and each one has their strengths and weaknesses depending on what you're trying to get out of it. So with VE, why we've leaned into this is it's such a versatile tool to calculate so many different things on a building project that an architect might need to know about early in the design process, because it's going to affect the envelope of the building, the selection of various materials and fenestration windows, lighting, things like that. And it also works fairly seamlessly with the workflow architects already have, where we build three-dimensional virtual models, digital models of a project that we need for obviously, creating the spaces and making sure we can accommodate, the various programmatic functions for a client, solving the sort of puzzle of space planning for a building. But even in those early stages now, we can start to do things like solar studies and even airflow studies. If we have an idea that we might have natural ventilation for a project, that we can start to put in some very simple windows and kind of see how air would flow through a space, through that sort of dynamic modeling. There's actually standards that have been developed by ASHRAE now that are starting to help evolve the practice of building performance simulation, both from the standpoint of engineers and architects. And so we're starting to teach to these standards, and they kind of inform, different stages of the design and development process. Architects are generally mostly concerned with, on this diagram, the first 3 cycles of modeling for a project, or creating a virtual twin of the future building. So we teach our students, simple box modeling, which is this top icon up here, which is where we basically just have, maybe a very simple geometric form. We haven't really created a roof yet or anything like that, but we can, place it on the proposed project site, orient it different ways to see the solar impact, to see how, maybe the wind's going to affect natural ventilation schemes. And it's going to start to inform things like the generation of the roof, generation of shading, things like that. So as we move further into the different modeling cycles and we start to develop the concept further, the model becomes more detailed, a little bit more elaborate. The elements in the model start to know what they are. Walls begin to understand what their U values are. What's the heat transfer through them? Things like that. We even start to introduce preliminary, HVAC systems, heating, ventilating, air conditioning, and can start to, even reduce the loads early on in the conceptual design of a project by sort of knowing how the environmental factors are influencing the loads on the HVAC system. Are we having to overcool a certain space because it's got too much solar radiation, or vice versa? Do we have areas that we're always going to have to heat because they don't get any kind of natural day lighting? And so early on, we can actually start tweaking the envelope when we have the ability to do that in a much easier way. We also do lighting studies, both natural and artificial electric lighting. So, in a situation like this, which is like a little restaurant, there's a variety of lighting coming in. Obviously the natural day lighting from the windows on the left. We have various, electric lighting for the dining area, which is a certain, kind of aesthetic quality to it. And then even back in the food prep area, where there's different, code implications or code criteria that has to be addressed. you know, Up until now, until recently, as an architect, we would have to wait to have a conversation with a lighting designer, electrical engineer, before we could really kind of get into a qualitative design or assessment of the light levels. But now, with the software, we can look at whatever the target, foot candles are, whatever the light levels are, the illumination for a space, depending on its use. And we can use the software. In this case, we use the ISVE Radiance tool, and we can do some pretty elaborate ray trace illumination studies in the virtual model. So we can see what the various foot candles are at different surfaces, from different parts of the space. We can detect glare, so we can see where glare is going to be an issue. Maybe we need shading. And interestingly enough, as we've been doing it, with our students in the classroom, we actually place virtual sensors in the spaces in the same way we would have a light sensor in a room to detect when there's lighting levels, so they can actually dim the light so that we're not over lighting a space. And so we do that in the virtual model in the same way we'll do that in the real space, so that we can predict the energy consumption of lighting for that space. Same thing with airflow. Through the dynamic modeling, we can simulate airflow, whether it's coming in from the outside and we're doing a natural ventilation scheme. We can find out, how many cubic feet per minute of airflow we get coming through a particular window or through a space. And that's really important for a variety of reasons, that if we need to naturally ventilate a space, that we have a broader comfort range, for the conditions inside the space, that people are more tolerant of a broader temperature range, a little bit broader humidity. And so by simulating that, it sort of allows us to sort of verify or confirm that natural ventilation would be an appropriate and a code compliant method for a building project. In more critical facilities, like for instance, an operating theater, like we can see here, where airflow is critical on so many levels, as far as not only bringing oxygen to the people in the space, but also making sure we have sufficient ventilation to get any kind of toxins or pathogens out of the space. By doing this modeling virtually, it really informs the sort of confidence of how the building's designed, the mechanical systems that are being proposed. And to be able to see it visually is really helpful for sort of fine tuning it to make sure that the owner kind of gets the outcome that they're looking for this type of a space. And then where we take this, even early on in a project, with our students, we've been, simulating various systems, lighting, airflow, things like that, and then also even doing photovoltaic production simulations. And so we can do a predictive, assessment of what's the energy use intensity for a project. So in this case, say the project is 40 kBTU per square foot. We can then make sure that we're, accounting for a photovoltaic generating system on the roof or on site that's going to meet those needs, so that we can, early on in the project or in the design development phase, actually try to balance out the consumption and the production of energy for a project, so that we're not just bringing solar in, at the 11th or 13th hour on a project, but it's actually an integral system, on a project. So the solar vendor or who's ever going to be designing that system would be a part of the collaborative team early on. With all this technology, though, we also have to be kind of careful, because time is obviously one of the limiting factors for a lot of projects. They're always very time dependent as far as having deadlines. And so when we work digitally, we've got to, be very aware of what we call level of detail, not investing too much time in this virtual model in ways that we don't reap benefits from. So that's a skill that a lot of architects and we teach our students to be aware of. Only sort of investing time in things that you get some sort of a positive benefit from. And then, of course, resiliency is another aspect of energy modeling and simulation that is becoming ever more present. It's something that's not necessarily easily qualified financially, but we've seen, with particularly throughout the United States, the sort of vulnerability of communities to, fires we have here in Southern California, flooding all throughout the United States, tornadoes, hurricane events, things like that. How can we use this technology of performance simulation in a way to help make buildings more resilient? So, for instance, here in Southern California, where we suffer quite a bit from the heat island effect, where we have a lot of extreme heat days, that Los Angeles County has one of the ways that they've tried to address this in buildings is to have regulations that say, when a project, and this could be recently they passed an ordinance requiring apartment buildings in Los Angeles that are built, from this point forward, that if the power were to go out for a 2-day period, that the interior conditions inside that space cannot get above 82 degrees Fahrenheit. Well, that's great to have that kind of regulation, but how does the building team actually confirm, in the design process that that's possible? And so with performance simulation, we can actually predictively model that. So we can, through natural ventilation, through the various construction assemblies for a project, the orientation of the building relative to solar heat gain, we can predictively model what would be the interior conditions inside a space. And so this diagram, which shows air temperature inside a room annually, that we can see it in the peak periods, that, although there might be a few days where we actually get above the threshold, that at least helps us to isolate, okay, on those days, maybe we need to, shield a little bit better against the sun that we might experience in late August or September, or reduce the, the fenestration that would be in, the direct solar radiation beam. But it's really interesting to see how we can actually now, through data and science, climate science, actually provide some sort of confirmation of that performance, whereas it would have been, much more elaborate and involved calculation process, a much more manual process, 15, 20 years ago, to say that, an interior space would meet certain, environmental uh, performance levels. So I think with this introduction, what I'm really trying to stress for the architecture profession, and what we've tried to teach at College of the Canyons, is that the architectural design process is going beyond just simply baseline code compliance. We're obviously trying to pursue net zero energy goals. There's sustainable rating systems like LEED and WELL that a lot of projects try to pursue. But more importantly, is that for clients, who see the building as really more of a tool, an instrument, a means to an end, if you will, to achieve what their goals are. If it's in the case of a hospital, it's obviously serving patients. If it's a school, it's teaching students. In an office building or a house, it has those objectives. That architects can now use building energy modeling and performance simulation in a much more direct way to help the clients confidently achieve what those outcomes are that they're desiring for that project. So that's my kind of overview. Be happy to answer any questions that anybody may have.
Jason, this is Gabby. I have kind of a quick question for you, I think. So in your program, so do you use this throughout your program, or is it in an individual course, or how do you use this in with your students? So
That's a good question. So, and it's developing in real time.
Okay.
So in our Bachelor of Science program in building performance, we've tried to introduce students to this sort of performance simulation tools early on. So, um, for instance, in the spring, I teach an environmental control systems class. And so we start using the tools within Revit, which is a software program that the students are already familiar with. They're already building their virtual models in there, but we start to then look at some very basic metrics like, EUI, energy use intensity. We don't necessarily get down too much into the individual space, but that the constructions that they're defining in the model and the geometry has an influence on what that EUI is going to be when we plugged in some very generic air conditioning systems and electrical systems, lighting, things like that, so that they're at least aware that there's actually a data output that they need to start being aware of, and that as they make design decisions, it's not just solving kind of the client's needs for spaces and views and access and things like that, but they also have these considerations for energy efficiency. And then as the next semester, then we have a building energy modeling class, which is much more dedicated to this. And so that's a lecture lab class where we teach the IESVE software, and it's in tandem with their design studio project. So our students are doing a nature center project. And so early on, as they're doing some very simple block diagramming, they're starting to figure out kind of where the spaces go in the building, and trying out just different variations, that we actually do some very early what we call shoebox modeling, just to see what is the performance differences if we rotate the building this way or that way, or we start to bring a roof in that's sloped this way or that way. And then as they continue to develop and add more detail to the design, they can get into the more sophisticated modeling like airflow and artificial lighting, things like that. So the idea is that, yeah, throughout, basically from this point forward, they're going to be using these tools in their design process.
And then the software itself, so at the college, so I know softwares can be expensive. So does the college subscribe to the softwares? And are they expensive? I mean, and
Yeah,
how does that work? And I don't know if we can share that information.
yeah.
Yeah,
So
how does that work exactly?
let me pull up that slide that I had that kind of lists some of the different softwares.
Because I know
Uh,
that's always useful information, but I don't know to what level that can be shared.
Yeah, so interestingly enough, a lot of the for students, almost all this software is available for free. Um, Generally, in our case, we reached out to several of the software publishers, and because we're an academic institution, they provide a certain number of licenses. They're trying to, obviously get, a foothold in the industry. And that's a business practice or business model that Autodesk, which is the Goliath of software programs in the building industry, they've used for decades. They want students to learn the software so that when they go out into the industry and start working at firms, that that becomes the entry point for that software at a firm, which is where these companies obviously make their money. But most of these are also freely available. So like some of these bottom ones, Energy Plus, Cove Tool, those are publicly available. They're built off of some of the calculation engines that the Department of Energy and NREL has created over the years. So um, they're not as intuitive or as graphic as far as the interface that some of these other softwares are, but they still will give you the same end results. It's just more spreadsheet based sometimes, or not as visual.
Okay,
Yeah.
I think that's pretty helpful to everybody. So there was also, we had in the chat, Jen Clemens and Tiffany. So Jennifer Clemens said, along those lines, do you have a specific program you prefer, or you teach a variety of programs, vendor agnostic, so that students are comfortable with several types of programs?
Well, we definitely don't want students to be dependent on any one platform, because they're going to go work for a firm that might use something that's different. So we make sure students have an exposure to at least like 3 or 4 different softwares that are 3D modeling, or even in the case of the building energy modeling, we've been using the Revit, we've been using ISVE, and we're going to be going into Energy Pro in the second half of the semester here, just to provide them with that sort of versatility. And also the different softwares approach these simulations from different vantage points. So there's an educational benefit from doing that. You kind of see a dimension of let's say airflow simulation that you wouldn't have seen by using another method.
Yeah, that makes sense. And then Tiffany says she feels like this information is great to cross-pollinate the electrical and construction students, improved education of building design for different trades. Do electrical and construction students also take a course that gives some substance to these concepts of energy efficiency?
So that's a really great question. And I think that's where the industry, the AEC industry, architectural engineering construction, is trying to move in that direction of this sort of much more direct collaboration between the different trades. At our school, our architecture students are required to take construction classes. We don't really have an engineering program here, but I mean, that's obviously depending on the school, could be an option as well. The thing is with our industry, though, it's obviously very competitive in the way that a lot of buildings project contracts are structured. It's almost set up to be sort of adversarial. And so in order for this technology to be really effective, it requires all the stakeholders, all the players to share information, to kind of work together collaboratively. But in doing so, it sort of leaves you open to liability exposure. And that's the part that, people kind of shy away from. That, if I were as the architect to develop a model and, to work on it concurrently with, the contractor, or to hand over the model to them, how reliable is that model for their use? Are they going to have to spend time cleaning it up or getting it set up for their needs? And a lot of that, the sort of granular details haven't necessarily been worked out. Not they've been worked out technically, but sort of contractually. There's no one entity that oversees all this that can kind of dictate this is how it should be done. And so I think that the industry kind of suffers as a consequence. So we're trying to do our part from the bottom up, and hopefully, through the students, they become the Pied Pipers that kind of, help this gain traction, this collaborative process.
Yeah, and Jen says maybe not possible in the scope of a class, but has there been any research or data validation on how accurate was the model to an actual building construction energy use?
That's a great question too. Yeah, because like how reliable is the information you're getting from the modeler? So when we developed our curriculum 2 or 3 years ago, when we were starting to really lean into building energy modeling, had a variety of conversations with educators at the Cal Polys here in the, as well as at UC Berkeley. And also one of the software liaisons, if you will, is a professor at San Francisco State University. And so as we've talked and kind of decided what platforms we're going to use, we felt very confident with, particularly this VE software, because it has been, there's been about a decade or more of kind of verification research that's gone into, the predictive modeling and how does that actually translate to real world conditions. It is one of only 3 softwares accepted by the California Energy Commission to be used for Title 24 energy compliance documentation. So that shows the level of vetting and rigor for a software. So that's one of our metrics, is if we can't use this software to teach students about code compliance documentation because the state won't accept it, then clearly it's maybe not as vetted or as rigorous as another software platform. So that's a good question. And that's always the sort of confidence that a client, would be hesitant to, really stake their, their money and their reputation and, this project on, is like, okay, if we're going to pay for all these additional services or these, these things, how confident are we that it's actually truthful? And, there's some track record, but obviously because a lot of this technology is still emerging, It's going to only have to get more and more robust as we go on. More and more examples of, proofs, if you will.
All right, I've got one from Ken. He said he was curious about the photo you shared of the older building with the unusual avant-garde shape with like a big yellow wing. We have a building kind of like that from the same area. I'm curious if you know for these and other unconventional designs, what is the long-term operation and maintenance cost of those facilities? I am just thinking that it might be very hard to find things like replacement windows, doors, and other materials for those types of structures. For schools that have those kinds of experimental buildings, are these still considered to be cool? Or do some of them turn out to be headaches for the building managers?
So let me make sure I get the right image that Ken's referencing. I don't know if was it this retail project?
That wasn't the one I was thinking of. It was sort of,
That
yeah, there
one.
you go. That was
Good.
the one right there.
Okay,
Yeah.
hold on.
Go
I don't
back.
know if that's actually an avant-garde building or not, but that was the one I was
Yes.
This
thinking of.
this one here?
Yeah.
Oh, so this is the same exact project though.
Oh, okay. I didn't
Just from a
realize.
different
Yeah.
angle.
Okay.
Yeah.
Just
Yeah,
from a
it's just
different view.
it's a
Yeah.
more dramatic angle. Yeah. So an interesting I'll go forward a couple slides to this one here. This is a retail center. It's a speculative retail center, meaning the developer didn't have tenants lined up when he built it. It was designed, I think the design went from about 2006 to early 2008. Um, and it was designed with a variety of passive, sustainable features. But one active feature that the architect, and I was the project architect on it, that we'd incorporated was the idea of a motorized shade device that would basically allow the upper band of windows to be shielded from the sun, when appropriate. And unfortunately, that right as the project got permitted, the 2008 recession hit, and all the building projects literally came to a halt. They all were put on ice. This developer decided to move forward with this project. I think they had signed a lease with a couple big tenants like Circuit City and like Trader Joe's or something like that. So they felt pretty confident, but they were going to value engineer the heck out of the projects. And so one of the first things to go was this motorized shading device. And so it was a lesson learned for us that, you got to be careful because you may design things to work a certain way, but if for some reason like a value engineering decision gets made, that actually created a vulnerability for the project. So now it actually, in certain times of the year, overheats, or the mechanical equipment has to work more than it would have if we'd known about that decision earlier on. So in a way, although this building looks kind of, sort of futuristic and all that, a lot of the systems are pretty conventional. The aluminum and glass storefront system is bread and butter. It's all plaster exterior construction. There's a little bit of custom steel, but it does bring up a good point that we talk to students about, of are you going to go into active mechanical systems that might do things, for instance, if we want to do a natural ventilation scheme, are the windows, actuated? Are they motorized so that they open and close automatically based on, sensors and a building automation system? Um, and that's great, but those systems they need to be maintained and they break down. And what happens if they don't open up or they don't work? And so we stress, much simpler, more passive ways to do things that don't rely too much on, mechanics. But if you do, then try to keep things real conventional. Yeah, try not to get into anything too exotic because ultimately, it becomes something that's not maintainable or expensive for the client to maintain or replace, and ultimately is not seen as a uh, long-term wise decision.
Yeah, no, we've seen that with some projects in the Midwest that used like building integrated photovoltaics where the solar panels are forming part of the facade or part of the roof, which is great when it's brand new. But then if the panel fails 10, 15 years later, like trying to find a replacement for them is really hard. So you end up with an
Oh,
array
yeah.
that kind of like half produces electricity and hopefully isn't, leaking too much airflow if it's the case of a, part of your building envelope. So yeah, it's always a challenge, you know, like how far out on the leading edge do you want to go with these new materials and new designs
Yeah.
versus how careful do you have to think about the person that's got to maintain the building over time, right?
Yeah. And students, they'll see in the magazines or on the websites, projects that use like thin film PV and, stuff like that. And, it's great because it integrates with the architecture. But, as we know with it, it's been proven that PV systems last, seemingly forever, longer than most roofing systems, And so, you want to kind of keep it simple with the understanding that that PV system could be there for 35 years, and if anything, it's only going to be replaced because not that it may not work, but that because the efficiencies have improved such that it makes financial sense to go with a more modern system.
Yeah, we were just looking at some of the new panel warranties the other day. There's firms out there now that are warranting their PV panels for 40 plus years, which is pretty remarkable.
Hmm.
It makes you wonder if the firm will still be around in 40 years to honor the warranty, but it's pretty remarkable that they have that kind of confidence in their product, you know?
Absolutely, yeah. And so buildings obviously require maintenance, in at different time scales and in different materials and systems, and so that's something that comes into the conversation with a lot of students, but a lot of times that's learned in the profession, and unfortunately through hard knocks, with client, either renovating buildings where you can kind of see evidence of what decisions that were made early on that weren't very smart, and that the building is deteriorating because of it, or in the case of this high technology, where they leaned a little too heavily into something that was maybe an emerging technology that wasn't really mature yet, and maybe in the long run was discarded or failed. We've seen with like with solar hot water systems, that maybe the technology wasn't great 30 years ago, and those systems lasted for a little while and then have just been kind of sitting on a roof. Um, but more modern technology maybe doesn't suffer from, some of the same pitfalls.
Remind me sometime, Jason, if you come visit us in Wisconsin, I'll take you to our Portage campus. We've got a building that was designed for solar hot water heating on that one. It's a
Hmm.
wild looking building, but it hasn't generated any heat in a long time. So,
Yeah.
yeah.
Yeah, and they
We
did
get
that at
questions about it all the time because it's so unconventional looking, you know? Because
well, and
the
they did that at Lane Community College up in
You read my
Eugene.
mind, Jason.
Yeah, because they
yeah.
have this vertical facade element, which kind of shades the glass, so from a shading element, but it's looks really expensive, and it was a solar hot water system. I'm not sure how effective it is, but
I think I know the one you're talking about with
Yep.
the evacuated tubes. Yep.
exactly. Yep.
Yep.
I don't think it was working the last time we were up there, and that was, I don't know, 12 years ago, I think.
Yeah.
So, any other questions? Oh, can you talk a little bit more about the LA Max indoor heating rules and where you see this going?
So this is an interesting one. We approach this in two ways in our classes. So now that we can do predictive modeling, we look at the specific LA County requirement, which is 82 degrees at the 2-day peak period annually. And it's not just air temperature; it's what's known as set temperature, so standard effective temperature. So it takes into account humidity and things like that. Um, and so all apartment buildings are now required to meet that standard in LA County. Well, that's, when they build, I don't know, 20,000 new, apartments, spaces per year, that's a lot of work for an energy modeler to verify those things. In commercial, we don't have a requirement yet, but we do hit that in the lead rating system. So in school projects or government projects or anything that's trying to go after the lead rating system, they have a similar requirement during an extreme heat event. The thresholds are a little bit broader. The temperature can get up to 86 degrees, But, if you think of a building that's not really designed to function without air conditioning, it doesn't have operable windows, that's a really hard goal to accomplish, when it's 110 degrees out. And so it almost mandates that you have ways to evacuate heat, and that ability to model that performance is really critical. That's the only way you can actually sort of inform how to do a passive building to achieve those results during that, that extreme heat event. There's a lot of pushback, obviously, from developers. The fact that LA County passed the regulation on residential units was, obviously met with a lot of, sort of political pushback, lobbying, but they saw it as a life safety issue, that people die, in an apartment that doesn't have air conditioning, that overheats during these extreme heat events. A lot of people have nowhere else to go. They can't necessarily get to a cooling center or something like that. So I think, as climate change continues to worsen, global warming, then we're going to probably see that mandated, at least in California, for a broader swath of projects.
I think that's pretty fascinating. I hadn't heard of that.
Yeah, it's a fairly new one. Just this last year went into effect. And, obviously there's a lot of developers that specialize in, large scale residential. And we're starting to see a lot more density because the governor just signed a law allowing for building densities that are in some ways off the chart as long as they're within walking distance of a metro station. So like in LA Times, you were, sort of predicting, well, what will we see? And so areas like Chatsworth, which is really just like a suburban, single family home neighborhood, we're going to start seeing 8 or 9-story buildings, in those areas because there's a bus, the Orange Line.
Yeah. You've got some thank yous in the chat, Jason.
Well, thank you all. I very much appreciate it. Yeah, we're, this is all sort of new academically. None of the other schools, even the universities, are only sparingly teaching this stuff. We have USC, the dean of the architecture school at USC is going to be coming out to College of the Canyons in a couple weeks with the chair of their building science program, and they want to kind of see what we're doing in comparison to what they're doing at the graduate level at USC. Because it's sort of cutting edge for them as well. So it's kind of neat to be doing this, but it really requires a lot of attention to make sure that we're not going off on tangents or, that we're always meeting industry needs, that we want to make sure that the students are getting skills and knowledge that, they can apply, once they go to work, for an employer.
It's impressive that you can be doing at the college what they do for $75,000 a year at USB.
Yeah.
I won't tell anybody.
Yeah.
So,
No, it is kind of exciting.
yeah. Well, I wanted to thank you for today, Jason. This was really great information. And I wanted to thank everybody for joining us today. And we hope to see you all online soon for our next webinar and our next Create event. And with that, have a great weekend.
Thanks, Jason. Bye, everybody.
Thank you all.
Bye. Thanks so much.
Thanks, everybody.
Yeah.